Okay, hello, everyone. I am Yuki Kambara, first grade PhD student supervised by Kosukubo-san. Actually, in this talk, nothing escapes from the system, but it is important as the initial condition of the later simulations or later studies. So maybe I can skip this slide, but the planet formation starts in the protoplanetary disk, and that coagulation leads to the planetesimal formation. Planetesimals are kilometer to 100 kilometer size solid particles. And after the planetesimals are formed, they gravitationally interact, and collision leads to the growth of planetesimals, and they form the protoplanets or planetary embryos. And after the protoplanet formation, they undergo giant impacts, the gas fusion, and some processes, and finally forms the planetary system. So, and this work focuses on this planetesimal evolution process. So first, where are the planetesimals formed? In the standard scenario, a minimum mass Nebula model, the classical works assumes that the planetesimals are formed all over the disk, and their initial distribution assumed to be smooth, like this smooth disk. There are no gaps, no substructures except for the snow line. But recent model calculations have shown that the planetesimal formation can occur only in the narrow ring region. And this results in the formation of rings of planetesimals like this. Okay, so after the formation, how do planetesimals evolve? There are several theories of planetesimal evolution, but they are based on the smooth distribution of planetesimals. And when we assume the smooth distribution of planetesimals, the planetesimal diffusion is negligible, and the surface density of planetesimal sigma is constant during the evolution stage. Under this assumption, it is known that the oligarchic growth of protoplanets occurs. This is a simulation result by Kokubo-san and Ita-san in 2002. This shows the semi-major axis and eccentricity of particles, planetesimals of planets in the simulations. And the size of each plot corresponds to the size of the protoplanets or planetesimals. And as time goes on, a small number of protoplanets can get massive. And also each protoplanet has the similar mass. The mass of protoplanets is estimated using isolation mass, which is proportional to the 1.5 square of the fifth power of the surface density. And also the protoplanets keep the orbital separation. They are very separated. The typical orbital separation is 10 times of Hill's values. Okay, so we know the case of smooth distribution. So how about in rings? Due to gravitational interaction, planetesimals can change their orbit by mutual scattering or something. And at the edge of the ring, planetesimals can be scattered away or leak away from the ring. And due to this scattering, the ring expands and the surface density of planetesimal decreases. And let's remember that the isolation mass, it depends on the surface density of planetesimals. So the growth of planetesimals in rings would be different from the smooth planetesimal disk due to planetesimal diffusion. So the final goal of this work is understanding planet formation from planetesimal rings. And in this work, we focus on the evolution process of planetesimals in the planetesimal ring. So when we have the initial surface density distribution of the planetesimal disk, we know the planet's mass using isolation mass as a function of initial surface density and the major axis. So we are trying to make the similar thing. So we are trying to formalize the mass or orbital distribution of protoplanets formed from planetesimal rings. And those distribution functions can be used as the initial condition of further n-body simulations or statistical models. So we are trying to formalize the protoplanet distribution. And for this purpose, we performed a series of n-body simulations starting from a planetesimal ring like this. There's a central star, and the planetesimals are distributed in narrow ring regions. We use a simulation called GPLAM, which is an n-body code for planetesimal system. And we calculated all the mutual gravitational interaction between planetesimals and with the central star. At first, we start simulation with a ring of planetesimals in the terrestrial planet region in the solar system. So the central star is 1 solar mass, the ring radius is 1 AU, and we distributed something like 100,000 planetesimals in the ring. And we systematically changed the total mass of the ring and the initial ring width, this width of the ring, and investigated dependence on these initial values. And in the fiduciary model, the total mass is 2.1 Earth mass, which is comparable to the sum of terrestrial planets in the solar system. And each planetesimal has 10 to the 20th gram, which is 250 kilometers in radius. And also we consider the interaction with the gas disk. We assumed the sink power law gas disk profile and gas drag force due to aerodynamical drag force. And for now, we ignore the type of migration and also the gravitational interaction with the gas disk. So here we show the overall results of the simulation with initial with 0.2 AU and the total mass is about 2 Earth mass. We show the same major axis and the eccentricity in the of each particles. Blue circles show the planetesimals, and red circles show the protoplanets, which are more massive than 1,000 times of initial mass. And initially, the planetesimals are distributed in this Xiang region, narrow region. But so we start from this start. So initially they are in a narrow region, and after the protoplanets are formed, they scatter planetesimals efficiently, and the ring width efficiently expands. And during their growth stage, a small number of protoplanets are growing larger, so that protoplanets are growing through oligarchic growth scheme. And also they keep the orbital separation typically about 10 to 15 times the Hughes radius. And their typical mass are 10 to the 26 to 27 grams. And also to investigate what determines the protoplanet mass, we plot something like this. We plot the same major axis and mass of the protoplanets here. Each blue point shows the protoplanets formed in the simulation. And the orange line shows the isolation mass without planetesimal diffusion. And you can see that the protoplanet's mass in the simulation is more than one order smaller than the isolation mass without diffusion. So we can say that diffusion is important. And we also plot the isolation mass calculated using the final surface density in the simulation. That is a blue line. And we can see that this matches well with the protoplanet distribution. Okay, so we can say that the surface density evolution due to planetesimal diffusion is important in a planetesimal ring. Then we checked the initial width dependence. We compared the 6 models with the same total mass, but different initial widths. From 0.025 AU to 0.8 AU. And the right animation shows the results. The top panel shows the results with the narrowest ring, and the bottom one represents the widest one. And the growth schemes are similar. So the protoplanets grow through oligarchic growth while the ring expanding. And also, initially, they are very different ring widths, but the narrower rings expand more dramatically than the wider one. And as time goes, their widths convergence regardless of the initial width. So we can see from this plot, the ring width time evolution, we plot the time evolution of the ring width. Initially, the ring width is more than one order different, but the ring width is converging as the system grows. This is due to the faster expansion of narrower rings. And in the narrower rings, the surface density of planetesimals is higher. And this causes the protoplanets to form faster. And the protoplanets scatter planetesimals more efficiently. Then this more efficient scattering causes a faster expansion of the narrower rings. Okay. We also compare the protoplanet distribution. We plot the major axis and mass of the protoplanets in the simulations with different initial widths. And different color shows the results from different initial widths. So first, we highlight the initial width, the results from initial width smaller than 0.2 AU. In this case, we can see that the mass and orbital distribution of protoplanets do not depend on the initial width, although the initial width is something like one order difference, 0.2 and 0.02. So we can say that protoplanets' mass and orbital distribution do not depend on the initial width in this case. And when the initial width is wider than 0.4 AU, the maximum mass of protoplanets is smaller when the initial width is wider. This is due to the initially small surface density. So when the surface density is small, the protoplanet cannot grow as massive as the higher density region. So this results in the width of the maximum mass. Okay. Finally, we show the results comparing the dependence on the total mass. So we compare three models with the same initial width, 0.2 AU, but with different total mass, 1, 2, 4 Earth mass. And they also, the protoplanets also grows through the oligarchic growth, and while the ring expansion are also observed in all simulations, but the more massive ring expands faster. The bottom panel shows the most massive one, and the top panel shows the less massive one. And we can see that the more massive ring expands faster, and the protoplanets are larger in the more massive ring. This is also because the surface density, so in the more massive ring, surface density is higher at first, so they grow faster, and they scatter planetesimals more efficiently than the expands faster. Finally, we compare the maximum mass of protoplanets when we change the total mass of the system. Each point shows the results in the simulation, and this blue line shows the isolation mass without planetesimal diffusion. We can also see that it is the simulation results. So the protoplanets in the simulation is one order less massive than the isolation mass. So when we change the total mass, the planetesimal diffusion and ring expansion is still important in this case. And without diffusion, the protoplanet mass is proportional to the 1.5th power of the surface density. So with the same width, it is proportional to the 1.5th power of the total mass, but the dependence on the total mass is slightly weaker than on the surface density. This is because the more massive rings expands faster, so the surface density decreases more faster, and this weakens the dependence on the total mass. Anyway, the planetesimal diffusion is important even when we change the total mass, and also the more massive planetesimals are formed in more massive rings. So this is the summary. We investigate the evolution of ring-distributed planetesimals, and protoplanets growth is the oligarchic growth while the ring expands. And as a future work, so we are developing a growth model on planetesimals and also especially the surface density evolution of the system. Thank you.
Pretty cool stuff. I have a quick question. You mentioned earlier on that you tested different resolution. Was there any difference when you had, was it 50,000 versus 200,000 particles?
This is not the resolution dependent. So we want to fix the resolution so that we change the number of particles when changing the total mass.
Okay, so you have the same mass planetesimals, we change the number of them.
Yes, yes.
Just wondering.
So so do you have any implication for the free floating planets? So that you calculate different from the different initial condition. The initial condition affect the rejection rate or something?
Actually, nothing is during the estimation because there are plenty of gas in this space. Still plenty of gas in this space. So yes, we need more the further calculation after this stage. So yes.
Thank you, Ernesto. So, this terrestrial planet formation is likely to will happen in the narrow waves. So maybe even though the paper Shima application, the paper applications. So if you simulation result apply for this kind of scenarios, so can you have some kind of constraint in the initial size of the narrow waves or in the initial mass of the narrow wings in order to reproduce the orbital architecture and the terrestrial planets in the solar system?
Change the initial width and mass of total mass. Yes, so with changing the initial width, we cannot change the planet distribution. So I think the initial width makes no change in the results. But so with changing the total mass, the planet mass is different. So the
initial width of the narrow wings may change the final location of the protoplanets. So which means that I think the final location of the protoplanets should be affected by the initial size of the narrow wings. Is it right?
I think it's not right because this shows shows the position of protoplanets. So the position of protoplanets also do not depend on the initial width.